So I think I said in the original tutorial, and I always start out by telling kids, limits are not tough, they're weird. When you wrap your brain around them, they're actually pretty plug and chuggish, but wrapping your brain around them is a bit weird. And also, we need to talk about why we do limits. So why were limits invented? Isaac Newton, when he invented calculus, didn't use limits. They came along about 100 years later to put calculus on a firm mathematical footing. What is your eventual goal in calculus? Why did Isaac Newton invent calculus? Isaac Newton wanted to find the slope of curves. So here's a curve. Let's make it a little better, Mr. Dewick. Something like that. You know how to find the slope of a line. If I say to you, slope is what over what? You're all going to say rise over. You've all heard that before. Yes? In fact, you've even seen the slope formula. Slope is y2 minus y1 over x2 minus x1. But that only works for a linear function, for a line. How the heck can you figure out the slope, you with me, of a curve? Well, Isaac Newton said, it seems to me if I zoom in to this curve, it resembles, if I take a tiny chunk, that looks more like a straight line than a curve. It's still a curve, but they said, what if I zoom in on this chunk? I could zoom in so much that eventually this looks like a line. Even though it's a curve, it becomes the same math as a line. And then I can use my slope formula. Now, he said to do this, I'm going to modify my slope formula. I'm going to use function notation. I'm going to use the concept of y equals f of x. Sorry, I should say he didn't use function notation. We choose to use function notation because it makes it cleaner. And now you can get kind of a generic slope formula. Let's suppose I wanted to find the slope between 2 points. I'll call this x1. I'll call this x2. Then I guess x2, x1, instead of y2 and y1, I'm going to say this is f of x2, the y value that you get when you plug in x2. And this is f of x1, the y value that you get when you plug in x1. That's still y2 minus y1. You made it look more complicated. I did, but I made it more flexible. Then Isaac Newton said, I would like x2 and x1 to get closer. This is how we'll zoom in mathematically. So instead of being this far apart, I want them to be that far apart. No, closer. No, closer. No, even closer. You know how close? Until they're 0 apart. Until this is 0. Problem. Can you divide by 0? No. Answer. You can take a limit as that distance approaches 0. This is why limits were invented by mathematicians. It was to put calculus on a firm mathematical foundation. If you want to know how you take the slope, you take the slope of a curve, and you'll see this in a few days, or you may have seen it already, by going like this. The limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Or you may see the notation written a bit differently. But this is saying, look, start out with your x value, go a tiny bit past it. How tiny? So tiny that that's 0, but not. Find that height. There's your y2. Find the height of your original point. There's your y1 divided by x2 minus x1. Well, if I go x plus delta x minus x, the x's cancel, I get that. Take the limit as that approaches 0, and now you're finding the slope of a curve. Have you seen that before already yet or not? Okay? Oh, and then next unit you'll learn all sorts of shortcuts so that you can do this in your head. Trust me. So what is a limit? The best definition, I stole this from another website, but the best definition I saw of a limit, how high a graph, by the way, I'll print this up for you if you stick around till the end, or I'll post this online, or fire me, if you have to leave early, fire me an email. I'll email this to you when you're done. So you don't have to write this down. A limit is how high a graph would like to be. If it could. What do I mean by if it could? Well, let me shrink this down a tiny bit. Here's a graph. Make this way smaller so I can fit it on here. Here's a graph, okay? I want to look at when x equals negative, Mr. Dewick, negative 1. When x equals negative 1, decide, but can you see there's a hole in the graph? This graph is not defined at x equals negative 1. What about the limit? Well, how high does this graph want to be right there? Pretty clearly negative 2. That's the limit. Let's go in a bit more depth, a bit more detail. If I take the limit as x approaches negative 1 from the left, what height am I approaching? So from a graph, I can read limits graphically, negative 2. If I take the limit as x approaches negative 1 from the right, oh, and what height am I approaching? This is negative infinity? I think not. What height am I approaching? Okay, probably want to put those on. What height am I approaching, folks? Negative 2. Did I get the same value approaching from either side? Then we say the limit exists. If you get the same value approaching from the left as you do approaching from the right, then we would say the limit as x approaches negative 1 from either side, who cares, equals negative 2. Okay? Which limit would not exist? Hey, Owen, right here at x equals negative 3. Because notice if I approach from the left, what height am I hitting? 0. If I approach from the right, what height am I hitting? 6. Are those the same values? We would say that limit does not exist. The left-hand limit exists, 0. The right-hand limit exists, 6. But the limit itself doesn't exist. Sorry for those of you on YouTube, but I often kind of imagine moving my fingers along the graph. And if they end up touching, the limit exists. If they don't, no limit there. Does this limit at x equals 1, 2, 3, 4, 5, at x equals 5, does it exist? Nope. Oh, what about right here at x equals 3? The limit, in fact, is 1. Yes, from either side. And the function also happens to be 1. Unlike this one here, where at negative 2 the function doesn't exist, but the limit does. Here, the function has a value, 1, and the limit exists. So that's why I said how high a graph would like to be. Oh, if it could. It can't be that high because apparently there's a hole in the graph for some reason. But it clearly wants to be that high. Is that all right? So, What about, let's look at this weird example here when x is negative 3. The limit as x approaches negative 3 from the left is 0. The limit as x approach, gotta get my notation right, as x approaches negative 3 from the right is 6. So, the limit as x approaches negative 3 equals what? It's a trick question. Oh, is it turned off? It's a trick question. It's a trick question. What does it equal? Have you seen that abbrev yet? Okay. So that's an example of a limit that does not exist. Where will limits not exist? Whenever you have something shoot to negative infinity and positive infinity in the same location. Okay? If they both shot up to positive infinity, we would say, yep, my fingers are meeting. The limit exists. It's positive infinity. Or if they both shot down to negative infinity, we would say, yep, my fingers are meeting. The limit exists. It's negative infinity. Is that all right as a bit of a start? So if you have a graph, you can really evaluate a lot of these. You had a quiz, right? Quiz. Here it is. You've also learned about, piecewise functions. How the heck do piecewise functions work? Are you okay on piecewise functions? People are nodding. Sarah's nodding. Yeah. If not, just say so. I'll do a couple. You okay on those? Basically, you graph that when x is greater than to the right of 0. When x equals 0, I guess you're 5 high. And when x is less than 0, it's going to be a parabola opening down. So whoever did this one, lovely. And you've learned the difference between a hollow point and a shaded in point to indicate which value is actually the function and which value we get really, really close to, but we never touch. Yeah? Okay? From this quiz question here, were there any questions you wanted me to go over? The second quiz, you said you had a bunch of questions, or we'll talk about that. So let's look at this then. The limit as x approaches 1 from the left. Here's x equals 1 from the left. 1, 2, 3, 4, 5 high. As we approach 1 from the right, 1 high. Does the limit exist? No. Does not. The limit as we approach 8 from x equals 8, 1, 2, 3, 4, 5, 6, 7, right there from the left. You know what? That limit is going to exist because it's on a continuous line. This is also why you've now heard the term continuity, I think. Yes? Because if you know it's continuous, then the limit is going to be there. There's no holes. The limit will exist. It's when there's discontinuities, like right here, or like right here, or like right there at that specific point right there, or right here. That's where we have to be much more careful and talk about whether a limit exists or not. And again, why are we talking about limits? We want to eventually let limits approach 0. We want to divide by 0 without technically dividing by 0 so that we can find the slope of a curve. Do the following limits. Do A, B, and C algebraically. Use a graph for E, F, and G. Okay. So, excuse me. If I'm evaluating limits analytically, algebraically, I think I got some here. The first method is stick it on your calculator. So let's look at this one here. It says take the limit as x approaches 0. Okay. First thing I always try, either in my head or on a calculator, plug it in. 0 squared minus 25, close bracket, divided by open bracket. 0 squared minus 4 times 0 minus 5. Apparent limit of this is 5. No problem. When are we going to run into problems? When is this going to become an issue? Well, it would become an issue if we had this. The limit as x approaches 5 of x squared minus 25 all over x minus 5. Why is that an issue? I'm going to end up dividing by 0. Okay? One way I can do this, now I can get this by factoring, but one way is to use that left-hand, right-hand trick and sneak up on it. Instead of plugging in x equals 5, I can always go maybe 4.99. Bracket 4.99 squared minus 25, close bracket, divided by 4.99 minus 5. And if I go 4.99 squared minus 25 divided by 4, am I plugging in a 5? No, but I'm sneaking up on it from the left. What do I mean by from the left, Owen? A little bit smaller than 5. I'll bet you the answer is going to be 10. I can try the same thing, but instead of 4.99, I can go 5.01. Sneak up on it from the right. Are we converging to the same location? This limit exists. If you're ever doing like a crazy limit where I have no idea what to do, that calculator trick, sneaking up on it, will work all the time. It may be some fairly heavy-duty typing, but that will at least tell you what the answer is supposed to be. It's not necessarily a proof, but at least you know where you're going. Okay? How would I evaluate this one algebraically? What would I do? Looking for a word that starts with letter F. I'm going to factor. Okay? I hope you've been taught this, but when it comes to factoring, what's the first thing that you always, 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 I could keep going another 100, always look for? Don't you always check for first? Always? Always. Always. Because if you're lucky, you can pull something out and make the rest of the terms smaller and easier to factor. Here's next to the fourth. There are ways to factor x to the fourths. But maybe I don't need to if I can pull out a few x's. What's the next thing you do? The next thing you do is not so obvious, but what you should do is count terms. Because if there's 2 terms, can't put a minus there. That looks. Let's go like this. 2 terms, question mark? There's only one thing you know how to do. There are other 2-term factoring. There's something called sum and difference of cubes, but we don't teach that in our curriculum, so I don't think Mr. Camozzi is going to throw it at you. If there's 2 terms, the only thing that works is what we call difference of squares. Hey, there's a subtraction sign, perfect square, perfect square. If that doesn't work, it doesn't factor. That does not factor. If there's 3 terms, there's 2 possibilities. It could be something like this, x squared plus 7x plus 12, where you're looking for numbers that multiply to what and add to what? Multiply to 12 and add 2. By the way, if you haven't figured out, you're going to have to get good at factoring for this unit. It really helps. Holy smokes, I didn't think it was that useful. Yeah, it is. Or, if it's really yucky, you might have something like with a leading coefficient. 5x squared, or I don't know, plus 11x plus 2. Why are those yuckier? You can't quite do these in your head as easy. There's something called factoring by grouping or a box method, but you got to be able to handle those. If you want to, I can teach you how to do that. But for now, Owen, back to you. How did you say we're going to do this? What's 5 plus 5? Like we found when we snuck up with our calculator. Okay? Going back to your quiz. Nope, going back to your quiz. So, here, for A, plug it in. For B, you're learning about the integer function. What does the integer function do? It's the greatest integer to the left. There's also something called, I think it's called the ceiling function. That's the greatest integer to the right. Always round up. Integer function, always round down. Right? Here, factor. Here, approaching 0 from the left. Now, if you know what the graph looks like, if you have a graphing calculator, or if you know what the graph looks like, great. But even if I did not, I would say, okay, I'm approaching 0. Did I say from the left? 0 from the right? I'm going to put a number in slightly bigger than 0. A little closer to 0 from the right. Ooh, what's the trend? It's shooting off to... So D, positive infinity. Ooh, what if I was approaching 0 from the left? Ooh, I think it shoots off to negative infinity to the left of 0. This is how I can start to figure out what this graph is going to look like really quickly. I also know how to graph these, but when in doubt, if you're not sure, calculator will bail you out quite a bit. So that's how I know those two answers. Oh, F. Is there an F? Oh, there it is. Did we get the same answer for both of them? Do our fingers meet when we follow along? Nope. The limit does not exist. Second quiz. Okay. So this one you said was a little bit yuckier. Which ones of these would you like me to go over? All? Okay. That's what I was wondering. Well, okay. Before I come back to this, hopefully you've learned that when you're taking limits to infinity, the largest degree term dominates. In other words, if I have this, the limit as x approaches positive infinity of 3x squared plus 2x minus 4 all over 2x plus 6. As x gets bigger and bigger and bigger, this 2x minus 4 is not going to make any difference. It's going to be minuscule. What's going to dominate is this larger degree 3x squared. You've all seen that? And here, what's going to dominate is the 2x. This limit will be really similar to, the symbol for is approximately equal to is a curvy equal sign. The limit as x approaches infinity of just 3x squared over 2x. Oh, one of the x's cancel. You know what? It'll be really similar to that, 3x over 2. If I plug an infinity into here, what will I get? What's the limit as x approaches infinity of 3x over 2? 0? Let's see. 3 times... If I'm trying to figure out infinity, I usually go with like 1,000,000, 10 to the 6th. Oh, don't need a bracket, Mr. Duke. Divided by 2. Is that 0? In fact, what is the answer? If we plug in a bigger and bigger and bigger and bigger and bigger number here, positive infinity, when would it be 0 if this x wasn't on the top, but instead was on the... Yeah, if I had 3x and 2x squared there starting out, then I would end up with 1 over x, like in one of your quiz questions. That would be 0. Is that okay? Ooh, what if it was this? Well, then I would end up with this. This graph, as you shoot off to positive infinity, eventually becomes 1.5 high. 3 over 2 is 1.5. So it gets either, I'd have to see what it looks like to see whether it shoots down to 1.5 high or shoots up to 1.5 high. But are you ready? An end behavior model for this graph, which is what you get when you let x approach positive or negative infinity. This funky graph is going to do weird stuff near x equals 0. I don't know what, but as I move out to positive infinity, it's going to resemble a horizontal line 1.5 high. Is that all right? Sarah, yeah? You gotta talk louder. First version, the answer would have been infinity because you had this. The limit as x approached infinity of 3x over, over 2. Well, look, the x is on the top as you put bigger. This is going to get bigger and 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 bigger. It's going to shoot off to infinity. If we had ended up with this, 0, a number. Now let's try this one here. As we shoot off to infinity, the real question is, what will this behave like? Well, first of all, we're putting in a positive number, getting bigger and bigger and bigger. What's the absolute value of a positive number? Yeah, this weird function here is going to be really, really similar to 2x minus 1 just over x minus 3. Because putting a positive 10 in there, that's just the same as 10 minus 3. You don't need the absolute value. It's not going to make a difference. Putting a positive 50 in there, the absolute value is not making any difference. It's going to be 50 minus 3. This graph here, if you're putting positive numbers in, is going to behave identical to this. Now let's take the limit as x approaches infinity. What's the degree of the top? An x. See it? What's the degree on the bottom? An x. Those ones will dominate. So this will start to behave just like that graph. The minus 1 and the minus 3 will not make a difference as you're getting bigger and bigger and bigger. Ooh! What happens to the x's? Was the correct answer, I hope, was it 2? Okay. Oh, just for giggles, unless it was on, let me check, it might have been on the quiz. Did they do, no. What if instead we went to negative infinity? We'll call it part 2. What if we did the limit as x approached negative infinity of 2x minus 1 all over the absolute value of x minus 3? If I put a negative into here, what's going to happen when I take the absolute value? You know what? It's going to turn into that. And that's because of how the absolute value function works. So we kind of applied our limit to the absolute value function by just saying, look, I know it's going to chuck the negative, so it's going to turn into, it's going to resemble, it's going to be like this. Then we applied our limit definition to say, well, look, the -1 and -3 are not going to make a difference. Take the limit as x approaches infinity. Yeah. Wouldn't the top one still be? Thank you, Owen. I haven't done this for a while. The top one would be negative because you're putting a bigger and bigger negative number in here. You're correct. I would actually end up with a negative divided by a positive. I would end up with this, but the top would be negative and the bottom would be positive. You're correct. It would be -2. Owen, I owe you a candy. I would have checked that as well. I would have really, really quickly gone, hey, what do I use for negative infinity? -1,000,000. I would have quickly gone bracket 2 times -10 to the 6th divided by 10 to the 6th. And I would have said, oh, hang on, I typed that wrong. 2 times -10 to the 6th divided by 10 to the 6th. And there you go. And just even by putting in 1,000,000, my calculator couldn't even keep track of the decimals, and it's 2. It's not exactly, but it's close enough that my calculator couldn't even track the decimals. And I said it's 2. It's -2. Owen, thank you. Thank you, thank you. I owe you a candy. Every quiz question. So B. Going to be kind of a similar concept with the absolute value thingy. Okay. First of all, will putting in a negative make any difference on the top? Will it make any difference on the bottom? So I would argue that this is going to be the same as that. The absolute value is not going to make a difference because everything is absolute valued. Now let's do the limit. Will that +1 make a difference at all? This is going to be the same as the limit as x approaches infinity of x over x. What's x over x? 1. Now, it looks like whoever did this kind of said, hey, those will cancel. I can get there in one step-ish. But there's the full thought process, okay? We have to be a little careful with, I'm always a little hesitant with limits because it's easy to make a silly mistake like I just did to go too fast. I go very meticulous. C. There's a star next to that one. What does the star mean? Oh, you had like 2 answers. I can tell you the answer. First of all, what does this mean? We're sneaking up on 2 from the. So 1.99. First thing I might do really quickly is I might go 1 divided by. Let's see if we can figure this out without our calculator. What are we putting in? 1.99. The top is going to be a 1. What about the bottom? If I put a 1.99, first of all, will the bottom be positive or negative? I'm going to get a positive divided by a negative. Yes? If I go 1.99 minus 2, it's going to be negative big or negative small? What's 1 divided by negative small? First of all, what's a positive divided by a negative? Negative. What's 1 divided by a really, 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 really small number? Yep. And if you don't believe me, you could actually try. 1 divided by bracket, let's go 1.99999 minus 2. And I get a negative big number shooting off to infinity. Is that okay? So I got to be honest. I would do it the way I just verbally spoke to you, especially if I was in the middle of my calculus years in my limit prime back then. I could do a lot of these pretty quickly, but you kind of get a feel for them. But you start to see why I said limits. They're not tough. They're weird. When you wrap your brain around them, they that kind of makes sense. D. Ooh. Well, I know what e to the negative x looks like as a graph, so I've got a bit of an advantage. I'm willing to bet you don't necessarily know what e to the negative x looks like as a graph. Do you? Okay. It looks, we're replacing x with negative x. That's going to be a horizontal reflection about the y-axis. It looks kind of like that-ish. So as we approach positive infinity, this is getting closer and 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 closer to 0. But what if you don't know what the graph looks like? That's a good question. What can I stick in as my analog or my temporary substitute for infinity? 1,000,000? Sure. Ooh, where's my e to the button on my calculator? So everybody get your calculator out, please. You all have somewhere an ln button, or we often call it ln. Somewhere you've got an ln button, probably right near your log button. You see it? Find it? Almost certainly second function ln is your e to the. If I go second function ln, now I'll come help you find it. So for this one, I think my analog would just be, so we all found our E button. Mine is second function ln. It's somewhere on your calculator. I would probably try E. If you try E to like the 1,000, you're going to get an error. Negative 1,000, you're going to get an error. I would probably try E to like the negative 99. And if you do that, you get a really, 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 really small answer. So it's 0. That's how you know that that one's 0. Or you can graph it. I know that as a graph, it does that. So as we move to positive infinity, further and further and further and further and further to the right, it gets closer and closer and closer and closer to 0. Because I know what exponential graphs look like. Yeah. For C? Oh, good question. If it was this, limit as x approaches 2 from the left of 3x all over x minus 2. Are we doing a limit to infinity? Then, you know what? We're going to plug in 1.99 and just see what happens. If this was a limit to infinity, then this would end up being a 3x over an x and the x's would cancel because the x's would dominate. We're not doing a limit to positive or negative infinity, so it should be, let me just see, 3 times 1.999 divided by 1.999 minus 2. Did I do that right, Mr. Dewick? Look, looks like it's still approaching negative infinity. Is it, Mr. Dewick? Yeah, because we're not doing a limit to infinity. We're getting closer and closer. Basically, what's affecting everything is this right here. Sarah, as you're getting closer and closer and closer to 2 from below, this is becoming a smaller and smaller and smaller and smaller negative number. So you're going to get a negative answer, but when you divide by a smaller and smaller and smaller and smaller and smaller negative answer, your answer is bigger and bigger, but negative. That's a terrible infinity. Is that okay? That was D. Let's go back to the quiz, Mr. Dewick. E. So find any vertical asymptotes. Show using limits. So you want me to do this one as well? Okay. So let's type this out. Find vertical asymptotes. Show using limits. I'm not going to do the one from the quiz. I'll make up one of my own. Let's go like this. Suppose f of x equals negative 1 all over x plus 2. Where's the problem? What can't we divide by? 0. What's going to make this work out to 0 in the denominator? Okay, so the issue, there's going to be an asymptote almost certainly at x equals -2. So let's go like this. Look at x equals -2. Here's my question. Do they both shoot off to positive infinity there? Do they both shoot off to negative infinity there? Does one shoot off positive, one shoot off negative? This is a job for limits. I'm going to sneak up on that -2 from the left. I'm going to sneak up on that -2 from the right. See what they do. That's what it means, show using limits. Pretty darn sure there's an asymptote there. There might not be. When might there not be? The other possibility is instead of an asymptote, you've just got a hole in the graph, right here. That's not an asymptote. There's a hole in the graph there. How would you notice that? If when you did left hand and right hand limit, you got the same value for both, and oh, that means it's not an asymptote. It's combining, converging right there. So let's do this. Let's take the limit as x approaches 2 from the left. I'm going to imagine 1.99999. On the top, -1. On the bottom, when I put a 1.99999 in here, will this overall be negative or positive? Negative. Big number or small number? If I go 1.9999999 minus 2, and by small, I mean really small. What's a negative divided by a negative? What's 1 divided by a really small number? I think as we sneak up on 2 from the left, it shoots off to positive infinity. And this is how my brain actually does these. I think positive or negative. Sarah, you're looking at me puzzled. Did I make a mistake? I think I'm right. -1 divided by bracket 1.9999 minus 2 plus 2, Mr. Dewick, plus 2. So I need to be putting in a negative 1.99. That's what you're saying? No. I forgot to look at the -2 right there. Is that what you're saying, Sarah? Yeah. Yeah! Thank you for catching it, at least. Hey, I haven't taught calculus for 10 years. I'm brushing the cobwebs off. So we would go like this, Mr. Dewick. We would go negative. Oh, from the left? What's just to the left of -2? Not negative 1.99999, but what? Yeah, boy, did I really botch this for you folks. Negative 2.0001. And then plus 2. That's what I'm imagining in my head. Approaching -2 from the left. So again, let's try that again. Top is still -1, yes? What's negative 2.001 plus 2? Will it be negative or positive? Big or small? Really small. What's a negative divided by a negative? What's 1 divided by a really small number? Yeah. So at x equals -2, to the left, the graph is shooting up to infinity. Positive. What about to the right? Limit as x approaches -2 from the right. Thank you, Sarah, for catching that. I was looking at the +2 like a meathead instead of looking over here. Duh. You can see one of the areas limits are tricky. You got to be really meticulous because it's easy to trip on your brain like I did. I wish I'd done that on purpose because that would have been a good learning opportunity, but I'm not that good. So it's going to be negative 1. In my brain, I think to myself, negative 1.9999 plus 2. That's what I'm thinking. First question. The top is still negative. What's the bottom going to work out to? Negative or positive? Big or small? What's a negative divided by a positive? What's 1 divided by a really, really small number? You know what? This graph does that just to the right of negative 2. I don't know what it does elsewhere, but I can tell you that. Find the vertical asymptotes. There is a vertical asymptote at x equals 2. I would say asymptote at x equals 2. Prove it. There. I snuck up on it from either side. And looks like it's shooting off to infinity from one side and shooting down. Yeah. Yep. Totally. Okay? What would 1 divided by a really, really, really big number be? 0. That's a horizontal asymptote. It's getting closer and closer to 0. Yes. And yeah, that's where the asymptotes come from, though. Does that make sense? Okay? Because I know later on, I think in the unit package, review package, you're going to get one of the things you're going to be asked to find are horizontal asymptotes. Okay. Let x shoot out to infinity, but instead you'll find, instead of getting a really big number, you'll get either 0 or you might actually get an answer. Let's keep going through the quiz and I'll tackle that. How long can you stay? Okay. Let me just pause for 2 seconds. So are you okay, Prav, with how I can find a vertical asymptote? Now, really, he could have just said asymptotes. Okay? How do you find asymptotes in general? Vertical asymptote, typically you're seeing if you're dividing by 0 anywhere. Horizontal asymptote, take a limit as x approaches positive and negative infinity, because that'll tell you what's happening out that way. Find the following limits. As x approaches 0. You all did Math 12 this fall. And so, in theory, you're supposed to remember your trig. And now, did I say trig? Gotta be in radians. Okay? What's the sign of 0? Probably in Math 12, in Pre-Calc 12 this fall, you probably did something called the cast rule, and you probably did the unit circle, and in theory, I hope you also did the sine graph and the cosine graph. Did you look at the sine graph and the cosine graph? Okay. Oh, some of you did it last year? Okay. What's the sine graph look like? It would be really, really cool if the sine graph looked like an S. That would be really, really cool. What's the cosine graph look like? It would be really cool if I turned my head sideways, turn your head sideways, 90 degrees, if the cosine graph sort of looked like a letter C. It doesn't quite, but close. Okay? Or the way my high school teacher taught us, cos rhymes with nose, and so he always just drew 2 eyes and a little face, and that's how we remembered the cos is nose graph. Whatever dumb way works for you. Okay? I told you, I am good at coming up with stupid ways to remember things. That, if you're asking me one thing I'm pretty good at as a teacher, that. So, sine of 0 is 0. Ooh. What the heck is that? Here, I think we're going to have to sneak up on the graph. Or did Mr. Kamosi give you a different way to do this? Okay? Because I noticed, is the answer 1? It's 1? Okay. So I think what I would do, because this one is one you've either memorized or you've graphed, I would go to it on my calculator. I would sneak up on it as a graph. I'm going to sneak up on 0 from the left. So I'm going to, first of all, make sure I'm in radians. Oh, stop that. Have been in radians for ages. Hello, my old friend. Radians are great. Radians are rad. Rad. Tough audience. Okay, and I would go sine. What would be a good number if I'm sneaking up on 0 from the left? Negative 0.0001. 3 zeros on a 1 divided by 3 0. Oh, negative 3 zeros. 3 zeros, Mr. Dewick, and a 1. What do you think we're approaching from the left? 0.9999999. Come on. Let's try that same trick from the right. If you're lucky, you can just backspace, delete the negative. Same answer both times? What's the limit? 1. I don't know of another way to get there without more trig than you know. Prab, is that okay? That's how I would have handled that one. And probably this next one very, very, very similarly as well. I would have said, okay, we're shooting off to positive infinity. What's my analog for infinity? Million. Honestly, though, 1,000 would probably do the trick. I'm probably overkilling. Let's do 1,000. Let's go sine of 1,000. Sorry for those of you on YouTube. I had COVID about a month ago, so I've got a nagging cough, but I'm doing fine otherwise. Are we getting a really big answer or a really small answer? I'm betting we're approaching 0. Let's go big or go home. Got a few more zeros. Small, you know what? This is probably 0. Yeah, there it is. I don't know of to evaluate this is not going to work because you're going to end up with these are both what are called 0 over 0 limits. You end up with 0 over 0. There's something that you'll learn called L'Hopital's rule. You don't know it yet. There is a way to actually evaluate that using L'Hopital's rule, but first you have to know how to take a derivative. You don't know how to do that yet. I doubt you're going to get one that ugly. But if you do, have I shown you a way you can handle it and get the answer? Okay. End behavior models. Okay. So an end behavior, yep. Okay. I'm going to do them anyways because I'm a nerd. I'll talk about it. I won't go through it. If we're doing an end behavior model, here's what it's saying. If you've got a graph that's acting all funky near the y-axis, near the center of the graph, it may smooth out as you go further and further out. It may behave like another graph. To find it, you just let x approach positive infinity, limit. Let x approach negative infinity, limit. And you might find, I'm getting something that, let me give you an example. One example of end behavior models. Because they're kind of cool. Suppose we have f of x equals 3x squared plus 2x minus 4 all over 2x plus 3. What's its end behavior model? What I would do is I would take a limit as x approaches infinity. And we're going to try and do this in our heads. What kind of a limit are we doing, Sarah? Infinity, which means when we're doing limits to infinity, the biggest degrees are going to dominate. No. I'm going to end up with, it's going to be approximately that. See it? One of the x's will, first of all, these won't matter at all. One of the x's will cancel. As this graph shoots off gets bigger and bigger to the right, it's going to behave, its end behavior model is going to be really similar to that. What's that a graph of? Line. Slope of? It's going to behave like y equals 3 over 2. It's going to eventually be going up 3 over 2, up 3 over 2. In the middle, there's probably all sorts of funky stuff going. I could find its end behavior to the left by taking the limit not to positive infinity, but to, okay? Sometimes you'll get a function. What if instead this had been that? Then I would have, that. You know what? This is going to behave like a parabola as you go further out. What if instead I had that? Well, then I would end up with that. As you take a limit to infinity of that with the x on the bottom, what will that approach? You're dividing by a bigger and bigger and bigger and bigger and bigger number. What are you going to get? Exactly as a number. Yeah. This is going to approach 0. As you move further out, it's eventually going to be parallel to the x-axis and infinitely close to the x-axis. So close you won't even be able to tell the difference, even though we'll know they're not quite touching. If you take the limit there, it'll behave like y equals 0. What if instead I had that? Then I'll have that. You know what? This will end up as the line y equals 3 over 2, which is a horizontal line 3 over 2 high, 1.5 high. It'll be behaving like a horizontal line. That's kind of the gist of end behavior models. They're really handy if you're wondering, hey, what does the graph look like way out there? What does it look like way out there? Do a quick end behavior model, limit as x approaches positive and negative infinity, and hopefully you'll see, I recognize what's left behind and know what it looks like. For the purposes of your course, you said Mr. Camozzi is not asking it. When I taught it, I did ask it, and I would tell them it's either going to be 0, horizontal asymptote, a constant, a height, or a line, or a parabola. I said, I'm not going to give you something worse than that, but okay, because those are all graphs you're pretty familiar with, right? They're old friends. And you said, so here's the right-hand behavior model, left-hand behavior model. For right-hand behavior model, let it approach positive infinity. For left-hand behavior model, let it approach negative infinity. This is a bit tricky with e to the x. You'd have to do a little bit of math along the way, but it would be doable. So that's kind of the two quizzes. Now, questions from your homework, from reviews or concepts that you would like me to go over, now is your chance to ask. Yeah. Nasaiba, you're first.
For the quiz, I actually had a question from that.
Yep.
For number 1, after someone to show this addition we're putting in, I was wondering if you'd
For number 1. This number 1? Piecewise function?
no, this
Second quiz. Okay, what did Mr. Camozzi show you?
I can just show you.
Okay, let me come look. So you were asking what's another way to do this one. What we're going to use is the idea that we know that the limit of 1 over x as x approaches infinity, this is one where we're approaching infinity, that equals 0. Okay? How can I get some of those to appear in here? Well, what I could do is I could divide everything by x. I haven't broken any equation solving rules because I've done the same. I've done everything to the top and bottom. Okay? Why is that nice? What's the limit of 1 over x as x approaches infinity? Gonzo. This is the proof. I was just saying we can ignore them. This is the proof of why you can ignore those numbers. Gonzo. Okay? Then he said, or he talked about, okay, what does this work out to? Well, because we're a positive number, keep looking up, kiddo. Because we're putting in a positive number, this absolute value isn't going to make any difference to a positive number, which means mathematically you can make an argument that it's really just that. What is x over x? What's 5 over 5? 1. What's 10 over 10? 1. What's x over x? 1. And so that's where this was now simplified to the limit. Oh, change colors, Mr. Duke. The limit as x approaches infinity of 2x over x all over x over x. That's a 1. Now we've gotten rid of all the x's. We've proved that the answer is 2. So that's a proof. And so we use that trick if we're doing a limit as x approaches infinity and you want to make things a bit cleaner. Specifically, you want to take advantage of, you proved this somewhere in your notes. So I turned those two into that gone. That's really what lets me say I know they're vanishing. So even, I got to be honest, technically, like some of these ones, really what I should have done if we were, oh, you know what? We didn't do a limit to infinity for either of these, so I was okay. But if I was doing a limit to infinity, I should have divided by x, divided by x, divided by x, divided by, and stuff would cancel and I can make some stuff vanish. But most of the time, once we've spotted the pattern, we say, hey, I spotted the shortcut. I know that when I take a limit as x approaches infinity of a polynomial, the biggest degree terms dominate. I'm just going to use that. But that's the proof of why. Is that all right? That's the proof of how come. Sarah, you had a question. Did you not, I think? Yep. Let me pause for a second. Number 1. Okay. I think I typed this one up. This looks like the way I format things. Alrighty. Where are there going to be vertical asymptotes? Where we're dividing by 0. Where are we going to be dividing by 0? I think I need to factor the bottom first. So the very first thing that I would do is I would say this is f of x. It's x plus 2 all over. What does x squared plus 3x plus 2 factor into? I'm looking for numbers that multiply to 2 and add to 3. Yes? Okay. You might think that we would have a vertical asymptote at x equals negative 2, but actually this simplifies. Those cancel. I'm going to have a vertical asymptote at x equals negative 1. I'll have a hole in the graph right there, but trust me, if I sneak up from, this would be at negative 2. If I sneak up on negative 2 from the left and from the right, I'll find the limit exists and it's a number. It's not infinity or negative infinity. Okay? So, here's my function. Clearly show how I would use limits to find any vertical asymptotes. So now, I know there's going to be one at negative 1 because I can't divide by 0. Now I'm going to go, okay, I'm going to take the limit as x approaches negative 1 from the left. I'm also going to take the limit, change colors so it's easier to distinguish, as x approaches negative 1 from the right. Of 1 over x plus 1. Sarah, let's see if we can do this intuitively in our head. If we're approaching negative 1 from the left, what's a number just to the left of negative 1? Negative 1.000001. Yes? Okay. So it's going to be 1 over. When I put a negative 1.000001, will the bottom work out to positive or negative? Really big or really small? Okay. There is going to be an asymptote that approaches negative infinity just to the left of negative 1. In other words, if I'm sketching this graph, there's negative 1. Just to the left of negative 1, we're doing that. Is that okay? What about just to the right of negative 1? Okay. I should put these in brackets. It's a little easier to figure out what all this calculus notation is. Well, the top is still going to be a 1. What's just to the right of negative 1? How about negative 0.99999999999999999, etc.? Yes? When I put a negative 0.9999 right there, will the bottom work out to positive or negative? Really big or really small? You're going to get a positive answer. When you go 1 divided by a crazy small number, you're going to get a crazy big number. What's the craziest big number we can get? So just for giggles, let me see if I can go to my Desmos software and graph this. I thought Chrome had crashed. Let's go to Desmos. Come on, calculator, you can do it. What was the function? It was, what was on top? Bracket x plus 3, 2, all divided by okay. Does that look about what I said? Oh, where was the hole? At negative 2. If I go to x equals negative 2, it's really, really tough to spot because how big is that hole? It's infinitely small. Because at negative 1.99999999999, the graph still exists. So you can't see it on here until I Negative 2 is what? There it is. Okay. By the way, this is a free graphing software that you can also download for your phone, right? The Desmos Graphic Calculator is pretty good. Out of the ones I've tried, it's the best one and it's free. Is that okay? I think that I would be okay with that. I would say you took a left hand and a right hand limit. You used your knowledge of limit rules to take some shortcuts. I'm okay with that. In university, they might require you, okay, how do you know this is true? But they would walk you through their proofs and exactly what they're looking for. They might say, well, prove that that works out to that. I don't, but you would have done that and been able to fall back on that. So in limits, what you typically do in university is you keep establishing more and more patterns or more and more. I can use this now. I can turn this yucky question into one I've already done. Is that all right? Next question. Owen, yeah. What types of discontinuities are there? So what are there again? Sorry. Discontinuities. There is, what was the first one you said? Okay, there's point. Jump. Okay. I didn't spell that. Oh, I did. Wow. Okay. From a graph or from a function? From a graph, it's usually pretty easy. I just showed you a point discontinuity. There is a point discontinuity. Right there. The graph, there's a hole. Okay? What would a jump discontinuity look like? As a graph, it would look like that. Okay? How do I come up with it? It would be a piecewise function. And so it would be a piecewise function where they ask you to take the limit right there from the left and from the right, and you noticed I'm getting two completely different answers. Okay? Is that enough of an explanation, or do you want me to actually make one up? I can try.
Question was y equals...
Where's it from? Hang on, let me pause. Here's hoping I can do this. I didn't actually look at the question. From page 80, number 7. So the instructions say, find the points of discontinuity and identify the type. And number 7 is y equals absolute value of x over x. Okay. I'm going to do a quick look and see what they want me to do here. Removing a discontinuity, continuous functions, finding a discontinuity. Okay. Where will this be discontinuous? Well, I think if I put in a 0. So this is a tough part for me to teach you, except to say, I've done a bunch of these. What would make the bottom work out to 0? Ooh, but what would that make the top work out to? Also, 0 divided by eesh. Okay? So I think now what I would do is I would take a limit as x approaches 0 from the left. I would also take a limit as x approaches 0 from the right. Okay? Now it says find the point of discontinuity. I would say discontinuous at x equals 0. They didn't specifically say tell me how you found it. They just said found it. There. I did it intuitively because I know you can't divide by 0. And it said identify the type. It didn't specifically say how I was going to do it. Honestly, I would probably kind of go to my calculator. But let's see if we can do this intuitively. If I approach 0 from the left, I'm thinking negative 0.00001. If I put a negative number here, it would just end up becoming positive 0.0001. Yes? Divided by negative 0.0001. I get that. I get the same thing on the top and the bottom, but negative from the left. Is that okay, Owen? What about from the right? Well, if I approach from the right, I'm going to get positive 0.0001 over positive 0.00. You know what? I'm going to get positive 1. You know what kind of a discontinuity this says? I guess at x equal, when we're on the left of 0, we're negative 1 high. When we're on the right of 0, we're positive 1 high. I think this is a jump discontinuity. Now, if I actually get some graphing software that lets me graph this will. Absolute value of x divided by x. Oh, look at that. Definitely a jump discontinuity. Everywhere else, not a problem. You'll either get the same thing over itself or the same thing divided by negative itself. Is that all right? That's kind of how I'd handle it. Oh, how do I know it's an oscillating? You're probably not going to get one. They're funky graphs. But what you would notice is, I don't know of a good way to identify an oscillating numerically. I can't think of one because I haven't done this for so long. I would identify it graphically by just graphing the function and say, oh, this is a weird one. And you've seen a few of those where they just keep swooshing in and zooming out. Right? Is that okay? Next. Yeah. So, if a discontinuity is removable or not, that's a good question. Supposing I wanted to remove a discontinuity for, I made one up, didn't I? Yeah, right here. This one. So let me go like this. Nope, better yet, Mr. Dewitt. Let's do it this way. Given f of x equals x squared minus 4 all over x minus 2. What, do you have an example of the question? I want to try and phrase it the same way they did. Let me pause. So rather than me making up an example, we're going to do one from the textbook. It's from page 80. What number was it, Prab? 20. We're going to do an even numbered one. Because you said that's what those ones hadn't been assigned. And so from page 80, we have a piecewise function. And typically, that's where you'll either have continuity issues in piecewise functions or functions where you're dividing by 0, but when you factor, stuff will cancel out. Okay? We have this. F of x equals 3x minus 2. No, 3. Really do it? 3 minus x? Wow. When x is less than 2. No, I'm reading the wrong. No, I started right. 2 when x equals 2. And x over 2 when x is greater than 2. So this is a point of discontinuity from a piecewise function. All right. It looks like everything to the, well, let's sketch this really quickly. I don't like the way this is written. If I was writing this in my notes, I would write it as negative x plus 3. Now it's in slope-intercept form. What is this going to look like? You know what, Mr. Dewick, you might want some graph paper. Thankfully, I have some up here. Copy. It's a one page. Sure, let's put it right here. So, typically when I'm graphing a piecewise function, I would often really lightly put the boundaries. When x is to the left of 2, when x, okay. So when x is to the left of 2, we're graphing negative x plus 3. That's going to be a function 3 high, 1, 2, 3, and it's going to go down, down. It doesn't or equal to, so there's a hole right there. Prab, is that okay? And then apparently x equals 2 when x equals 2. So right there. When x is greater than 2, I'm going to graph a half x. So that's going to have a y-intercept of 0, and it's going to have a slope of 1/2. It's going to be up 1 over 2, up 1 over 2, up 1 over 2. What's in the wrong place? The blue dot. So if you're asking me, how could I make this first of all, find each point of discontinuity, x equals 2. Then it says, which is removable. I could remove this if I redefined this as that. Now I'm good. Now that blue dot would be there. Now that blue dot would no longer be right here. Now it's a continuous function. That's kind of what is meant by a removable discontinuity. Let me give you a better example. This is the one that I was, let me see if there's an even numbered one there. The one that I was going to make up was something like this. F of x equals x squared minus 4 all over x minus 2. If I were to graph this, this is going to graph exactly like this. It's going to look like x plus 2, which has a y-intercept of 2 and a slope of 1. It goes up 1 over 2. Sorry, up 1 over 1, up 1 over 1, up 1 over 1. But where is this undefined? This is undefined right there at x equals 2. There's going to be a hole right there. As a graph, this would look like that. How could I remove this discontinuity? I could turn this into a piecewise function. I could say, oh, also, when x is not equal to 2, and how high does it want to be? There, I've removed the discontinuity by making it a piecewise function and saying that can get colored in. Is that okay? I don't know if Mr. Camozzi is going to give you those. Ask him, but I doubt it. Again, what we're really trying to do is get you to realize there are weird graphs out there. We can't just be casual. And if we're going to start dividing by 0, we have to be very, very, very meticulous. Also, we want you to realize the notion of a left-hand limit and a right-hand limit. That's going to come in handy because sometimes when we're looking at functions, we'll only have a piece of the function. We'll have to somehow check the ends. How will we check the ends? Well, on the right side, we'll zoom in from the left. On the left side, we'll zoom in from the right so that we know we're also checking the ends of a function if it's only a chunk. A little preview for you. Any others? No? Yeah. Number 14 from the same page? Okay. At what values of x is f continuous? I think we have to look at number 13. Oh, at that piece. So we're doing that main graph for all of number 11 to 18. Okay. At what? So number 14. So we're doing number 14 on page 80 for those of you who are scorekeeping at home. Sorry for those of you who don't know which textbook we're using. If you're watching this on YouTube, I apologize. Page 80, number 4. It says, use the function defined and graph. So for what values is f continuous? I'm going to flip the question. Where is it discontinuous? And it'll be all the other values. Look at the graph. You see where the graph is, right? Yep. Where is it discontinuous? It looks to me like it's discontinuous at x equals 0. Yeah, see it? Is that okay, Sarah? Yep. Where else? Where's the next one? Yep. Where else? I think x equals 2. Well, I'm looking at how the function is defined. It looks like the function actually isn't even defined at 3. I'm looking at all those domains that they wrote for the piecewise. I think they've defined this function as you don't include 3, so I'm not sure that's a discontinuity. It's not an actual hole in the middle of the graph. It's on the end. So I don't think I would include that, but I would certainly say it's discontinuous at x equals 0. It's discontinuous at x equals 1. It looks like it's continuous at x equals 2, but when you look really closer, there's a hole there. Discontinuity there. At x equals 0, that's a jump discontinuity. At x equals 1 and x equals 2, it's a point discontinuity. I don't see any infinite discontinuity. There's nowhere that shoots off to infinity. I don't see any oscillating discontinuities. Is that all right? Yeah? I'll take one more question if I need to, or we can end it. You've been very, very patient. I think if you watched the tutorial that I sent out, I probably did a more thorough job of limits specifically. I spent more time with you folks doing some of the weird specific calculus examples. I think in the other video that I sent out, I think I got into normal lines and tangent lines. Did I, Sarah? You watched it? I've been rewatching it, but I've got about 25 minutes to go, and I don't remember because that was 5 years ago. And heck, I don't remember half your names from last semester. So 5 years ago, I don't remember what the heck I did. But that might be one worth looking at. Last thing I would point out, 2 really good sites. PatrickJMT.com. That's Patrick, just math tutorials. He wrote Calculus for Dummies. So if you go there, I'm not going to video this. Pause.